Okay, so good day to all of you. So we're already in chapter 6, which is all about synchronization tools. So these tools are specifically used for processes that are executed concurrently. So let's start chapter 6. So again, chapter 6 is all about synchronization tools. So the contents of this chapter are background, the critical section problem, the Peterson solution, hardware support for synchronization, Mutex Locks, semaphores, monitors, liveness, and evaluation. So the objectives of this chapter are describe the critical section problem and illustrate a race condition, illustrate hardware solutions to the critical section problem using memory barriers, compare and swap operations and atomic variables, and demonstrate how mutex locks, semaphores, monitors, and condition variables can be used to solve the critical section problem, evaluate tools that solve the critical section problem in low, moderate, and high contention scenarios. So let's start this lesson by, of course, first is background of this lesson. So processes can execute concurrently. So they can be executed simultaneously. And this may be interrupted at any time, partially completing execution. So concurrent access to shared data may result in data inconsistency. So that is the problem with processes that are executed concurrently, because if they have shared data with other processes that also executes on their own, there is a possibility that it will have a data inconsistency. So maintaining data consistency requires mechanisms to ensure the orderly execution of cooperating processes. So illustration of the problem: suppose that we wanted to provide a solution to the consumer-producer problem that fills all the buffers. We can do so by having an integer counter that keeps track of the number of full buffers. So initially, counter is set to 0. It is incremented by the producer after it produces a new buffer, and is decremented by the consumer after it consumes a buffer. So let's go back with the source code for the producer. So while true, so it means that producer will produce a new buffer or an item in the next produced. So we have another while loop. So counter is equivalent to buffer underscore size. It means do nothing. So it means that why is it the comment is do nothing? Because the buffer is full. The stock for the producer is full. So since it is full, producing a new buffer will not affect anything. So that's why it will do nothing. And while if it's not full, so this will be executed. So buffer, the array buffer in is equal to next underscore produced. So the buffer produced by a new buffer produced by the producer will be included, will be added in the array of buffer. And then in is equal to quantity in plus 1 modulo buffer underscore size. So the value of this will be, the result of this operation will be stored in the variable in, and then we have counter plus plus. So counter is incremented. And then next is we have the code for the consumer for consuming the buffer. So while true, while counter is equivalent to 0, do nothing. Of course, how can the consumer consumes a buffer if the stack of the producer is empty? But if it's not empty, so we have next underscore consume is equal to buffer out. So the contents of the array of buffer will be stored in next underscore consumed, and then the result of the operations of out plus 1, quantity out plus 1, and then modulo buffer size will be stored in the variable out, and then counter will be decremented. So because of that, this illustrates the race condition for the consumer producer problem. So again, for counter plus plus, or we're going to increment the counter. This is used by the producer. So this code is used by the producer. It's coded in blue. So register 1 is equal to counter, meaning the value of counter will be stored to register 1. And then register 1 will be updated by adding another plus 1. and then this new value will be stored to register 1, and then the new value of register 1 will be stored in the variable counter. So this is for the producer and this is for the consumer. So we're going to decrement the counter. So this could be implemented as just the same with this one. It's only that producer 1 uses register 1 while consumer uses register 2. So it's just the same. So again, the value of counter will be stored to register 2. Then register 2 will be updated. So it will decrement a value, so or specifically 1. So register 2 minus 1 will be stored to register 2, and the value of register 2 will be stored in counter. So consider this execution interleaving with count is equal to 5. So the counter is equal to 5. So the value of counter will be stored to, okay, so the counter's value, which is 5, will be stored to register 1. So that's why register 1 is equal to 5. And then the next step is producer execute register 1 is equal to register 1 plus 1. Since register 1 is 5, you're going to add 1, so it will become 6. And then this new value of register 1 will be stored again to register 1. So the value of register 1 now is equal to 6. And then next is we have consumer execute register 2 is equal to counter. As you can remember, the value of counter is still 5. So that's why the value of counter will be stored to register 2. So that's why the register 2's value is still 5. And then the next step is consumer execute register 2 is equal to register 2 minus 1. So since the value of counter is 5 in the register 2, it will we will deduct 1. So that's why the value of the register 2 will be 4. And then of course, this will be stored in register 2. So that's why register 2 is equal to 4. And then next step, producer execute counter is equal to register 1, which is equal to 6, while so register 1 is equal to what? To 6. And then it will be stored to the counter, and then the register 2's value is 4, and then it will also be stored in counter. So as you can see with this last part, the counter should be the same. So if the producer adds a new buffer, it should also reflect with the consumer. And then if the consumer consumes the buffer, it should also reflect or update the producer that the consumer has consumed a buffer. But for this example, as you can see, why does the counter for register 1 is 6 while the counter for register rather for the consumer is 4. So there is the so-called race condition. So continuation for the race condition. So processes P sub 0 and P sub 1 are creating child processes using the fork function system call. So race condition on kernel variable next underscore available underscore PID, which represents the next available process identifier. So for this one, so P sub 0 creates its child process, and also P sub 1. And then the next underscore available underscore PID is equal to 65. So this is also a race condition because they both access the next underscore available underscore PID. So that's why it will return child is equal to 2615 for both of the processes. So unless there is mutual exclusion, the same PID could be assigned to two different processes. So that is the problem with the fork. It is also an example of race condition. So we have this critical section problem. So consider system of n processes from P sub 0 until P sub n minus 1. So each process has critical section segment of code. So process may be changing common variables, updating table, writing file, and others. So when one process in critical section, no other may be in its critical section. So the critical section problem is to design protocol to solve this. So each process must ask permission to enter critical section in the entry section, may follow critical section with exit section, and then the remainder section. So this is the structure of process P sub I for the critical section. So we have a do while loop, and then entry section, and then it will undergo its critical section, and then after it's finished its process in the critical section, we have the exit section, and then it will also execute other codes or other commands in the remainder section. So this is the, again, the general structure of process P sub I for critical section. So, what are the solutions to critical section problem? So, number one is mutual exclusion. If process P sub I is executing in its critical section, then no other processes can be executing in their critical sections. Number two, we have progress. If no process is executing in its critical section and there exists some process that wish to enter their critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. And then we have number three, we have bounded waiting. A bound must exist on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted. And then we have the following assumption that assume that each process executes at a non-zero speed and no assumption concerning relative speed of the n processes. Okay, so to further understand the critical section, so I'll give you a real-world example as to visualize this critical section. Assuming critical section is you're going inside a restroom. Specifically, assumption for the restroom, it's only, there is only one, of course, one toilet for that. So there are other restrooms that they have a number of toilets. But for this one, assuming one room and one toilet only. So for critical section, of course, this we have mutual exclusion. We have, for example, for you to better understand, as for example, if a person is going inside the toilet, so it illustrates that in this example, no one can enter because of course it's a private thing inside the restroom. Okay, so that is an example of a critical section for you to visualize this critical section. So if someone is inside, for example, the restroom, and then all other people who wants to use the restroom will have to wait for their turn. So I hope that this will better understand the concept of the critical section. Okay, critical section handling in OS. So two approaches depending on if kernel is preemptive or non-preemptive. So again, preemptive allows preemption of process when running in kernel mode. So again, for the term preemptive, for example, if a process is executing and then the other process who's next in the line has a higher priority, and then the process can preempt or interrupt the process in execution, and the second process will be the one to be executed while the first process partially completes its execution waiting for the second higher priority process to finish. And then we have this non-preemptive, runs until exits kernel mode, blocks or voluntarily yields CPU. So non-preemptive meaning disregarding of the priority, or if you are the first in the line, then you have to finish your execution first. So essentially free of race conditions in kernel mode. So non-preemptive is safer than preemptive because it will not yield or produce race conditions. So we also have this Peterson's solution. So not guaranteed to work on modern architectures, but good algorithmic description of solving the problem. So it has a two-process solution. So we have assumed that the load and store machine language instructions are atomic. That is, meaning atomic, it cannot be interrupted. So the two processes share two variables such as the variable integer name is turn, and then boolean flag. Then we have two values. So boolean, it's only true or false, the value. So that's why the content of the flag is only 2 elements. So the variable turn indicates whose turn it is to enter the critical section. So the flag array is used to indicate if a process is ready to enter the critical section. If flag I is equal to true implies that process P sub I is ready. So this is the algorithm for process P sub I. So while true, flag I is equal to 2, then turn is equal to J. And then while flag J and turn is equivalent to J, so it means that if it's um, process J's turn, example, and its flag is also true for J, so it will enter the critical section. And then if the flag is false, and then the process P sub J, for example, will exit the critical section and it will execute the remaining commands outside the critical section. So that's why we have this remainder section. So provable that the three CS requirements are met for number 1. So mutual exclusion is preserved. P sub I enters the critical section only if either flag J is equal to false or turn is equal to I. And then number 2, progress requirement is satisfied. And number 3, bounded waiting requirement is met. So although useful for demonstrating an algorithm, Peterson's solution is not guaranteed to work on modern architectures as it is stated in the previous slide. And then understanding why it will not work is also useful for better understanding race conditions. So to improve performance, processors and or compilers may reorder operations that have no dependencies. So for single-threaded, this is okay as the result will always be the same. For multi-threaded, the reordering may produce inconsistent or unexpected results. So that's why Peterson's solution is very effective for single-threaded systems, but for multi-threaded, the problem will be inconsistency and unexpected results. So for this, we have, so two threads share the data. So boolean flag is equal to false and int x is equal to 0. And then thread 1 performs while not equal or not flag. And then print x. And then thread 2 performs x is equal to 100 and then flag is equal to true. So what is the expected output? So 100 is the expected output with regards to the previous slide. However, the operations for thread 2 may be ordered. So for this one, first is you have to declare x is equal to the value of 100 will be stored to x, and then the value of true will be stored to the flag variable. So it is reordered. So if this occurs, the output may be 0. So the effects of instruction reordering in Peterson's solution. So for example, we have this one for process sub 0. So turn is equal to 1. And then flag 0 is equal to, for the flag for the process 0 is equal to true. And then it will enter the critical section. For process sub 1, turn is equal to 0. And then flag 1 is equal to true. It will also enter the critical section. So the problem here for the reordering, this allows both processes to be in their critical section at the same time. But as you can remember, for the critical section, we have this mutual exclusion in which only one process must enter its critical section and no other process cannot enter its critical section unless the process inside the critical section will finish its execution. So next is we have synchronization hardware. So many systems provide hardware support for implementing the critical section code. For uniprocessors could disable interrupts. Currently running code would execute without preemption, generally too inefficient on multiprocessor systems. So operating systems using this not broadly scalable. So we will look at 3 forms of hardware support such as memory barriers, hardware instructions, and atomic variables. So first is we have memory barriers. So memory model are the memory guarantees a computer architecture makes to application programs. So memory models may be either we have strongly ordered, where a memory modification of one processor is immediately visible to all other processors. And then the other one is we have the weakly ordered, where a memory modification of one processor may not be immediately visible to all other processors. So a memory barrier is an instruction that forces any change in memory to be propagated or made visible to all other processors. If the memory model of the system is weakly ordered, if you have a memory barrier, so this will force the change in memory to be made visible to all other processors. So it will be strongly ordered, which is of course forced because of the memory barrier. So we could add a memory barrier to the following instructions to ensure thread 1 outputs 100. So thread 1 now performs. So while not flagged, then we have the function of memory underscore barrier, then print x. And then thread 2 now performs. So x, the value of x will be changed to 100. And then again, there is a memory barrier to ensure that the changes will be available to all other processors, and then flag is equal to true. So next is we have hardware instructions. So special hardware instructions that allow us to either test and modify the content of a word, or to swap the contents of two words atomically or uninterruptedly. So we have the test and set instruction and compare and swap instruction. So this is the test and set instruction. So we have boolean test underscore and underscore set. So boolean pointer, the target here is a pointer. So the value of the pointer will be stored in boolean RV, and then the value of the true value will be stored in the pointer target and return RV. So test for this instruction executed atomically, or there's no interruption, returns the original value of past parameter and set the new value of past parameter to true. So solution using test underscore and underscore set function. So shared boolean variable lock initialized to false. So the solution, so for while test and set, we have the lock. So because it's locked, do nothing. And then we have critical section. Of course, it's like, of course, in the restroom, in the loo, if it is locked, no one can enter. If a person is inside and he or she locked his or herself inside the restroom. And then if the lock is false, and then of course the person is already finished using the loo or the restroom, and then it will for example, it will execute its other process and then while true. So again, I've used the analogy of using the restroom or the loo. Okay, we have another, the compare underscore and underscore swap instruction. So the definition, int, compare, and swap. So we have the parameters. So integer value, which is a pointer, int expected, and then int new underscore value. So the value, the pointer value will be stored. The value, again, the value of the pointer value will be stored in temp. And then if pointer value is equivalent to expected, so the new value will be stored in the pointer value and return temp. So again, number 1, so this is executed atomically, returns the original value of past parameter value, and then set the variable value, the value of the past parameter new underscore value, but only if the pointer value is equivalent expected is true. That is, the swap takes place only under this condition. So the solution using compare and swap. So shared integer locked initialized to 0. So while true, while compare and swap lock 0, 1 is not equal to 0. So it's equal to 1. So meaning, again, a process has already entered its critical section. And then if lock is equal to 0, then remainder section. So we also have the bounded waiting mutual exclusion with compare and swap. So for the previous slide, we've used the compare and swap. But for this example, this is a code if we included bounded waiting mutual exclusion. Okay, next is we have atomic variables. So typically, instructions such as compare and swap are used as building blocks for other synchronization tools. So one tool is an atomic variable that provides atomic or uninterruptible updates on basic data types such as integers and booleans. For example, the increment function operation on the atomic variable sequence ensures sequence is incremented without interruption. So increment, so we have this ampersand sequence. So this again explains that the increment operation and the atomic variable sequence ensures sequence is incremented without interruption. So ampersand here means that it is an atomic variable. And then the increment function can be implemented as follows. For void increment, atomic underscore int, then we have pointer v. So we have int temp and then do. So the value of the pointer v is stored in temp, while temp is not equal to compare and swap v temp temp plus 1. So we have mutex locks. So mutex, it's called mutex locks. Mutex from the word mutual and then exclusion, short for mutual exclusion. So previous solutions are complicated and generally inaccessible to application programmers. OS designers build software tools to solve critical section problem. The simplest is the mutex lock. So protect a critical section by first acquire function a lock and then release function the lock. So mutex locks use the functions acquiring a lock and releasing the lock. So again, it's like with the restroom and the loop or the loop. And then Boolean variable indicating if lock is available or not. Calls to acquire and release functions must be atomic or uninterruptible. So usually implemented via hardware atomic instructions such as compare and swap. So but this solution requires busy waiting. So busy waiting meaning, again, let's have an analogy, for example, in the restroom. Someone is inside the restroom. So for example, using the restroom. And then for example, you are in the line, or you are waiting for that person to come out. Since he hasn't come out yet, so you returned again. You return to, for example, you're doing something, and then you're going to return again to the restroom to check if it is already available. So that is for mutex lock. This solution requires busy waiting, meaning um, the process we're already talking about the processes. The process inline should always check if the critical section is already available to use. So that is why this lock therefore is called a spin lock. So again, it's just the same, busy waiting and spin lock. The processes must always check if the critical section is already available to use. Okay, solution to critical section problem using lock. So while true, so if a process acquires the lock, and then it will enter its critical section, and if it already finished processing inside the critical section, and then it will release a lock, and then if there are other codes or other commands that it needs to be executed, and then it will be executed outside its critical section. So mutex lock definition, so acquire, so this is the for the acquire function, while not available busy wait. So you have to check if the lock or if the critical section is available. So available is equal to false, since of course we can see here the exclamation point, meaning it's not available. And then release, so after the lock is released, then availability of the critical of the lock will be available, will be true, because the lock is already released. So these two functions must be implemented atomically, uninterruptible. So both test and set and compare and swap can be used to implement these functions. Okay, another one synchronization tool is we have the semaphore. Synchronization tool that provides more sophisticated ways than mutex locks for process to synchronize their activities. So Semaphore S is an integer variable, can only be accessed via two indivisible or atomic operation, which is wait and signal. For mutex Mutex Locks, it use acquire and release, while for Semaphore, it is wait and signal functions. So originally, in previous versions of this lesson, it is the function of P and V. But to be more descriptive, they used wait and signal. So definition of the wait function operation is we have wait for S, and then while S is less than or equal to 0, busy wait, and then S minus minus if it is equal or less than or equal to 0. And then definition of the signal operation, so signal S is we have S plus plus. So semaphore usage. So we have counting semaphore. Integer value can range over an unrestricted domain, or binary semaphore. Integer value can range only between 0 and 1. So if it is a binary semaphore, it will just be the same as a mutex lock. Can solve various synchronization problems. So what's good with semaphore semaphore is that they can have a unrestricted domain. They can have as many processes as they can acquire, they can service. So consider P sub 1 and P sub 2 that require S sub 1 to happen before S sub 2. So create a semaphore sync initialized to 0. So for P sub 1, so we have S sub 1 for P sub 1, and then signal, and then a semaphore sync, and then for P sub 2 wait, and then again the semaphore sync inside the wait function, and then S sub 2. So this statement just means that the condition that P sub 1 that require S sub 1 to happen before S sub 2. So can implement accounting semaphore S as a binary semaphore. So semaphore implementation must guarantee that no two processes can execute the wait and signal on the same semaphore at the same time. So thus the implementation becomes the critical section problem, where the wait and signal code are placed in the critical section. Could now have busy waiting in critical section implementation, but the implementation code is short and little busy waiting if critical section rarely occupied. Note that applications may spend lots of time in critical sections, and therefore this is not a good solution, because as we can see that it should have a bounded waiting, so meaning give other processes their opportunity to use their critical section. So semaphore implementation with no busy waiting. So with each semaphore, there is an associated waiting queue. Each entry in a waiting queue has two data items, such as the value of type integer and then pointer to next record in the list. So we have two operations. So we have block, place the process invoking the operation on the appropriate waiting queue, and another is wake up, remove one of the processes in the waiting queue and place it in the ready queue. So we have type def struct, so we have int value and struct process pointer list, and then we have semaphore. This is a data structure. So for example, we have for the wait semaphore, and then S will be decremented, the value is decremented by 1, and then if S value is less than 0, add this process to the S to the list and then block, and then signal semaphore, and then it's a pointer, so the S will be for value, it will be incremented. So if the value of S is less than or equal to 0, remove a process P from the list and then wake the process to be put to the ready queue. So what are the problems with semaphores? So incorrect use of semaphore operations. So for this one, so there is a signal for here and wait, using signal and wait with the same semaphore, and then wait and wait for another process. So omitting wait and or signal for the mutex. So this and others are examples of what can occur when semaphores and other synchronization tools are used incorrectly. So another synchronization tool is we have monitors, a high-level abstraction that provides a convenient and effective mechanism for process synchronization. It is an abstract data type, internal variables only accessible by code within the procedure. Only one process may be active within the monitor at a time, and pseudocode syntax of a monitor. So this is the syntax. So monitor, its monitor name, and then it's a comment, shared variable declaration, then function p sub 1, p sub 2 to p sub n, and its initialization code. So the schematic view of a monitor. So for this figure, so the monitor construct ensures that only one process at a time is active within the monitor. Consequently, the programmer does not need to code this synchronization constraint explicitly. So the condition variables, another synchronization tool. So condition X and Y. So two operations are allowed on a condition variable. So we have X dot wait function. A process that invokes the operation is suspended until X dot signal function. And then we have X dot signal resumes one of processes, if any, that invoke the X dot wait. If no X dot wait on the variable, then it has no effect on the variable. So if we're going to use a monitor with condition variables, so the x.signal operation resumes exactly one suspended process. If no process is suspended, then the signal operation has no effect, as stated in the previous slide. That is, the state of x is the same as if the operation have never been executed. So condition variables choices. So if process P invokes x.signal and process Q is suspended in x.wait, what should happen next? So both Q and P cannot execute in parallel. If Q is resumed, then P must wait. So options include such as signal and wait. P waits until Q either leaves the monitor or it waits for another condition, or signal and continue. Q waits until P either leaves the monitor or it waits for another condition. So both have pros and cons. Language implementer can decide. And then monitors implemented in concurrent Pascal compromise. And then P executing signal immediately leaves the monitor, Q is resumed. Implemented in other languages including Mesa, C#, and Java. So monitor implementation using semaphores. So these are the variables used. So semaphore mutex, so initially is equal to 1, and semaphore next initially is equal to 0. And then int next underscore count is equal to 0. So each function f will be replaced by then wait, then mutex, and then the body of f. So if next underscore count is greater than 0, and then signal next, else signal for the mutex. So mutual exclusion within a monitor is ensured. So for monitor implementation using condition variables, so for each condition variable x we have, so these are the variables. So semaphore x underscore sem initially is equal to 0, sem for semaphore. And then int x underscore count is equal to 0. And then the operation x.wait function can be implemented as x underscore count plus plus. So if next underscore count is greater than 0, then signal for the next variable, and then else signal for the mutex. And then wait x underscore sem, and then x underscore count decrement x underscore count. So the operation for x.signal can be implemented as, so if x underscore count is greater than 0, increment next underscore count, and then signal for the x underscore semaphore, and then wait for the next variable, and then decrement the next count. So resuming processes within a monitor. If several processes queued on condition variable x and x.signal function is executed, which process should be resumed? So the process here is the scheduling algorithm that we have previously studied, which is the first come first serve, frequently, but it's not adequate. So conditional wait construct of the form x.wait for C, and then where C is the priority number, process with lowest number, for lowest number means highest priority, is scheduled next. So next is we have single resource allocation. So allocate a single resource among competing processes using priority numbers that specify the maximum time a process plans to use the resource. So R means resource dot acquire T, so access the resource, and then R dot release, where R is an instance of type resource allocator. So a monitor to allocate a single resource. So this is the code for allocating single resource using a monitor. So we have, for this, we have the acquire and release. So next is we have liveness. So processes may have to wait indefinitely while trying to acquire a synchronization tool such as a Mutex lock or Semaphore. Waiting indefinitely violates the progress and bounded waiting criteria discussed at the beginning of this chapter, as you can remember, that mutual exclusion, progress, and then bounded waiting. So liveness refers to a set of properties that a system must satisfy to ensure processes make progress. Indefinite waiting is an example of a liveness failure. It means that for other processes who are waiting for their turn, they should be given opportunity to execute in its critical section. So also for in relation to liveness, so we have this deadlock. Two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting processes. So let S and Q be two semaphores initialized to 1. So P sub 0, we have wait S, and then for P sub 1, wait Q, and then wait Q command, and then wait S, and then signal S, then signal Q, then signal Q, and signal S. So consider if P sub 0 executes wait S and P sub 1 wait Q. When P sub 0 executes wait Q, it must wait until P sub 1 executes signal Q. As you can see, if it is wait for the other process, it should be signal for the other process. So however, P sub 1 is waiting until P sub 0 executes signal S. Since these signal operations will never be executed, P sub 0 and P sub 1 are deadlocked. So for you to understand deadlock, actually, there's a dedicated chapter for this deadlock. But for you to understand this concept, okay, let's have a real-world analogy. For example, student A and student B are having a simple drawing class. Both of them does not have enough resources. For example, student A has the pencil and student B has the paper. So, since both of them already has at least one resource to them, again, student A has the pencil, student B has the paper. Since no one is going to give in, for example, if student B, for example, shares paper, for example, this paper to student A, then student A will progress. Or the other, if the student A will give in and let student B borrow his or her pencil, then student B will progress. But since both of them are waiting for each other, who will give in, who will let them borrow each other's resources, so no one will ever progress to finish the drawing. So that is I think an easier example to explain deadlock. So for the processes, it's just the same. The process holds this resource, and then the other process holds another resource that is needed by the other, and they're all only waiting for the other process to release that resource. So that is the example of deadlock. So other forms of deadlock is we have the starvation or the indefinite blocking. A process may never be removed from the semaphore queue in which it is suspended. So starvation meaning the process in the waiting queue will never be executed in its critical section. So we have this priority inversion, scheduling problem when lower priority process holds a lock needed by higher priority process. So what does this mean? So, for example, if it is already the process turn in the critical section, then we have a higher priority that needs that resource. So what will happen? Will the lower priority process be finished first, or it will be or will it be preempted by the higher priority process? So priority inversion and starvation, it is solved via priority inheritance protocol. So what is priority inheritance protocol? Consider the scenario with three processes P sub 1, P sub 2, and P sub 3. P sub 1 has the highest priority, P sub 2 the next highest, and P sub 3 the lowest. Assume a resource of P sub 3 is assigned a resource R that P sub 1 wants, which is P sub 1 has the highest priority. Thus, P sub 1 must wait for P sub 3 to finish using the resource. However, P sub 2 becomes runnable and preempts P sub 3. What has happened is that P sub 2, a process with a lower priority than P sub 1, has indirectly prevented P sub 3 from gaining access to the resource. So to prevent this from occurring, a priority inheritance protocol is used. This simply shows the priority of the highest thread waiting to access a shared resource to be assigned to the thread currently using the resource. Thus, the current owner of the resource is assigned the priority of the highest priority thread wishing to acquire the resource. So, this is the end for our lesson in chapter 6. So, I hope that you learned something from this lesson, the different synchronization tools used in for process execution that is of course executed in concurrently. So if you do have any questions, please feel free to comment below, and please do not forget to like my channel. So again, thank you very much for listening, and good day.